Our focus standard for today's lesson comes from grade 7 Geometry Standard 2. Focus on constructing triangles from 3 measures of angles or sides, noticing when the conditions determine a unique triangle, more than one triangle, or no triangle. Our topic for this lesson comes from our Analyzing Geometry Relationships unit, Triangle Inequality Theorem. Our essential question is, what must be true in order for the 3 line segments to create a triangle? Please take a moment pausing the video if you need to, copy down the topic and essential question into your header, along with today's date, set your question column and your note column, and resume the video when you're ready to begin. We are going to be looking at triangle sides and looking at when we're given 3 different sides, can we determine when they'll make a triangle and when they won't. For example, here we have a triangle with the sides 3, 7, and 8, and we are being shown that they do fit together to make a triangle. Here on the right, we have 3 line segments, 5, 5, 10. And what we're showing here is that those side lengths cannot become a triangle. If you were to try and piece them together, there would always be an open side. Because they are 5 and 5, you might imagine that if you were to fit them together, they would collapse down and it would stretch from 0 to 5 right in the middle of this line of 10, and from 5 to the end would be this line segment. And that would fold completely flat and make a line, and that would not be a triangle either. So we want to start to analyze, can we determine, when given 3 side lengths, if it will make a triangle or not. Here I'm giving you the measurements for 3 line segments and groups of 3. So here's one for 2, 8, 9. And they are divided into categories. So this whole column, these 3 examples, I'm giving you 3 line segments, and I'm telling you that they do make triangles. Over here, I'm giving you 3 line segment measurements for each one, and I'm telling you that those 3 line segments will not make a triangle. So I want you to write these down, copy this table down, definitely leave some space, and see if you can figure out a pattern. What is unique about these sets of 3 numbers that is not true for these sets of 3 numbers? And this is our pattern analysis. The hint, I think, is in when we were talking about this one. We said we could connect these 2 5-unit line segments together, but if we did, they would fall completely flat. So notice, and it would be the same measurement as 10. Notice that 5 plus 5 is 10. And that doesn't make a line, doesn't make a triangle. Let's try something over here. All of the numbers are given to us in order from least to greatest. Did you notice that? Here they're all tied for the same meaning. And everywhere, least to greatest. What happens when you add the 2 lowest side lengths and compare it to the largest side length? So notice, like I said, we add 2 and 8 together, we get 10. 10 is greater than 9, that length of our third side. What happens if we try that with these 2? Interesting. If we add the 2 smaller sides, 6 plus 6 is 12, that is greater than the third side. 13 plus 13 is 26, and that's greater than the third side. What happens over here with these numbers? Have you tried that yet? Let's try that and compare. What do you notice? 2 plus 8 is 10, and that's exactly equal to 10. 6 plus 6 is 12, which is less than the third side. 20 plus 21 is 41, and that's less than the third side, 42 also. Over here, the sum of the 2 small sides was always greater than the third side. Over here, where they're not triangles, they're either less than or equal to. So I think we found our pattern. Does it hold for the two triangles that we started with? It sure does. 3 plus 7, the two shorter sides, are equal to 10, and 10 is greater than the third side, 8. So it makes sense that this makes a triangle. Over here, 5 plus 5 is 10, and that's equal to 10, not greater than. So let's take a look at what the triangle inequality theorem actually says. The triangle inequality theorem states the sum of any two sides must be greater than the third side. The way that we test this is exactly what we've done here. If you measure the two shortest sides and add them together, they have to be greater than the third side. If not, we know it won't make a triangle. Let's try and use this information to see if we can find the missing side lengths or possible side lengths or missing side on a triangle. Here's our problem. Two known side lengths on a triangle are 5 inches and 8 inches. Using the triangle inequality theorem, can you determine all possible side lengths for the third side? Well, we could test out in the trial and error with different guesses, but let's try and be a little bit more organized about it and use this information that we saw above in our pattern analysis. Here's how I like to think about the problem. First, I look at the two sides that I'm given and decide if those are the two shortest sides, how am I going to approach it? Well, what we just learned is that the sum of those two shortest sides would have to be greater than the third side. So I like to set up an inequalities statement. We can say that 5 plus 8 would have to be greater than x. X is representing the unknown side. Those are the two shortest sides. They have to be added together, and x has to be a number less than it. So what do you get when you complete this inequality? That's right. You would get that 13, since 5 plus 8 is 13, and that would be greater than x. So that side, if it is the longest side, has to be less than 13. What if 8 is the longest side? You know it's longer than 5, so what if it's also longer than the third side? Well, let's write an inequality for that too. If 8 is the longest side, then it would be over here on the right side of our greater than inequality. And we would know that 5 plus our unknown side length together have to be added together and be greater than 8. So let's use what we know about solving equations and inequalities to get x by itself. We can subtract 5 from both sides, since this is a positive 5. And what do we have left over? That 3 would be less than x, our unknown side. But 13 is the biggest number. So x has to be less than 13 also. So as one inequality statement, for knowing all the possible side lengths for that third side, we can say that x has to be greater than 3, but less than 13. And if we're being really precise, we put that all together in a complete sentence. The length of the third side would have to be greater than 3 inches, but less than 13 inches. And again, that's using what we saw in our pattern analysis above, and using the triangle inequality theorem. Let's try one more like that. Now we know the two known side lengths on a triangle are 6 centimeters and 12 centimeters. Using the triangle inequality theorem, can you determine all the possible side lengths for the third side? So I've given you the setup here, and you have an example to model this one after. Go ahead, pause the video here, and see if you can come up with the solution. Then check back when you're ready to compare your answer. How'd you do? In our final solution, you can see here that I got that x has to be greater than 6, but less than 18. And here's my work. If 6 and 12 are the two shortest sides, combined they make 18. So 18 has to be greater than that third side. if those are the shortest sides. But if 12 is the longest side, then 6 plus that unknown side have to be greater than 12. Doing a little work here to solve for x, we see that x would have to be greater than 6. So that's how I got to this solution, and I wrote out my answer in a complete sentence. That's going to conclude our work today on the triangle inequality theorem. Please make sure that your notes are complete, and we'll do more problems like this in class.